Hello, everyone. So today I will give a talk. The title is Efficient and Statistically Accurate Lagrange Data Assimilation of CIs Using Non-Interacting Flows. So this is a joint work with my postdoc Shubin Fu at University of Wisconsin-Madison and Dr. Georg Manucharian from University of Washington, Seattle. And this work is supported by the Office of Navy Research. So first, I'll give a very quick introduction about CIs, which you have seen many times during this workshop. So CIs is a granular material that has multi-scale features. Usually at very large scales, the CIs is modeled by a continuum for the viscous plastic rheology. While on the other hand, at smaller scales, these CIs will have brittle behavior with visible individual fragments, especially in the marginal ice zone. And that's why the discrete element method, or the DEM, is widely applied to describe the CI dynamics. So here, I show a very simple figure. In the left panel, you can see this is basically the Arctic sea ice region. And here you see this red box, which is about 400 kilometers times 300 kilometers. And when we zoom in, we see a lot of these fragments, and we call these sea ice floes, FLOES. And these flows can be modeled by the DEM method. And this will be the focus of our talk. So regarding the DEM models, these models these days become very popular because they have many computational advantages comparing with the traditional continuum models. First, these DEM models, in these DEM models, there's no need for an adaptive transport scheme to move flows between grid cells. And also, these DEM models can adaptively change the spatial resolution. So basically, it will bring us a lot of convenience for these models. And then with these DEM models, we also want to do some data assimilation. And because now our focus is on modeling each of these flows, so our coordinate will be the Lagrange coordinates instead of the Euler coordinate as in the traditional models. So the associated data assimilation is called Lagrange data assimilation. So in addition to recover the velocity field of these sea ice flows, we are also interested in recovering the ocean flow field underneath the sea ice flows. Actually, in the Arctic or in these sea ice regions, the observations for the ocean is very sparse or very rare. So it's very difficult to get the detailed information about the ocean. And especially there are sea ice just above the ocean, so it's hard for a satellite to get the direct observations. However, we can use these sea ice flows as our observations. Then we can use a coupled model between sea ice, atmosphere, and ocean. So putting these things together, we apply Lagrange data assimilation by observing the trajectories of these sea ice flows. Then we can recover the underneath ocean information. And this will be the focus of this talk. We try to do data assimilation under the Lagrange coordinate for the sea ice and for the ocean. Of course, Lagrange data assimilation is not a simple task because there are a lot of challenges of applying Lagrange data assimilation. So the first challenge is when we study sea ice, we have to take into account both the atmosphere and the ocean, because all these things, they are coupled systems. Well, if we consider all these three things together, then our entire coupled system will become a high-dimensional systems because we have to resolve the spatial scales at large scale, meso scale, and small scale. We need to take into account different variables in atmosphere, in ocean, and sea ice flows. Also, as I mentioned, we need to detect different spatial temporal scales. So the system, the coupled system, is also a multi-scale system. So to summarize here, we have a very complicated, high-dimensional, and multi-scale system to deal with when we try to do Lagrange data assimilation. And another challenge here is we actually have inconsistent coordinates. So for the DEM models, which are used to describe the sea ice flows, we use Lagrange coordinates, right? Because we try to track the trajectories of each flow. On the other hand, for the typical ocean and atmosphere models, we still use Eulerian coordinates. So how to put Lagrange and the Eulerian coordinates together will be a very difficult task for Lagrange data assimilation. And also, very different from the Eulerian data assimilation, for almost all the Lagrange data assimilations, we will suffer from strong nonlinearity when we deal with a coupled system. Because the model itself is nonlinear, so observations, which are the trajectory of the sea ice, will also be nonlinear. So all these things will be challenges for us to develop efficient Lagrange data assimilation algorithms. And in this talk, we will develop a new efficient and statistically accurate data-driven Fourier domain Lagrange data assimilation strategy to deal with the coupled atmosphere and ocean and sea ice systems. So before I discuss the details of this new algorithm, I want to introduce test models here. And the test model will be a coupled atmosphere, ocean, and sea ice system. So for the sea ice part, we use a recently developed DEM model. More information can be found in Georgi's talk or his paper. So basically, in this model, we try to describe two things. One is linear displacement and velocity, and the second is angular displacement and velocity of each sea ice flow piece. So here, the first equation is basically Newton's law. The time derivative of the displacement equals to the velocity. And here VCN means the velocity of each flow piece. And we denote the velocity at the center of each piece as this VCN. And then the second equation is basically it's F equals ma, Newton's law. So dv over dt is acceleration, m is mass, and this force F is the total forcing. And because sea ice is not just a point, it has certain shapes. So we need to do the surface integration of this forcing in order to take into account the total contribution from all these kind of forcings. And then the second set of equation is similar, but this describes the angular displacement and the velocity. So this capital omega is the angular displacement, and lowercase omega is the velocity. And this r is inertial, and the tau is the forcing. So in total, this F can be decomposed into the 4 parts here. And these 4 parts are the forcing from the ocean, forcing from the atmosphere, forcing from the pressure part, and forcing from the Coriolis force. And if we put the first 3 things together, then this formula will tell us how to compute the torque, the forcing of the omega part. So it's a cross product. And I do not want to discuss all the details here, but I want to emphasize that these 4 things are nonlinear functions of the state variables. So here we use a quadratic law for the drag force from both the ocean and atmosphere. So you can see here it's a quadratic form. So it's a nonlinear system here. And for each flow piece, we basically model it by polygons. And we'll assume it is a rigid body, just for this purpose of simplicity. Then for the ocean part, we use a 2-layer quasi geostrophic or QG equation with periodic boundary conditions. So I just summarize the equation here, but the details are not important. Basically, we'll have a 2-layer of the ocean, but only the top layer will have some drag force or interactions with the sea ice flows. And the only difference here comparing with the traditional QG equation is this term. And this is basically the feedback from the CIs. And again, I don't want to discuss the details, but what I want to mention is this ocean model couples with CIs. And we use the 128 times 128 spatial resolution of this QG model and to describe a 200 times 200 kilometer domain in the marginal ice stream in our study. And for the atmospheric part, here we do not use an idealized model, but instead we just take the real analysis data from ERA5, and then we only use the data at a large scale to describe the atmosphere. So we first get this data, then we adjust them to the double periodical domain for simplicity. Then we do a Fourier decomposition, but we only include 5 Fourier modes, 0, 0 mode, plus minus 1, 0, and 0, plus minus 1. So this will only describe the largest scale because in the Arctic regions, the observations of atmosphere are very sparse, also can be pretty noisy in the small scale. So we only want to focus on the biggest spatial scale for the atmosphere contribution here. So this is the idealized model we will use for the test. So although we said it's idealized, it's still mathematically still pretty complicated with a high dimensional system and all these multi-scale features. And this is just some illustrative figures. And in the top figure, you can see we have 2 panels. All these pieces are the CI's flows. So actually, we take these CI's flows from a library, and the library is based on the observations as a marginalized zoom. So these different pieces, they have different shapes, and they have different sizes. I show 2 dates, day 1 and day 3. And you can see because of the strong atmosphere wind, so within just 2 days, these CI's piece can move for a pretty long distance. And also they can rotate, like this has this shape, but now it rotates anti-clockwise to like 90 degree almost. So this is just model simulation. And these contour lines, if you can see, they describe the ocean flow field. And the stronger color means the local eddies is stronger than the other places. And we also show the energy spectrum and the vorticity spectrum of the ocean QG model. So for the energy spectrum, it peaks at absolute value of k equals 2 here. So absolute value of k means square root k1 squared plus k2 squared. And for the vorticity spectrum, it is a bit wider compared with the velocity. So actually up to k equals 10 or 11, still you have some energy. These are the small scale features which will also drive the CIs, especially for the rotation of the CIs. Okay, so now we will focus on describing the strategy for Lagrange data assimilation. So the basic method here we try to use is a localized ensemble Kalman filter, or LETKF, which is a well-known technique for ensemble Kalman filter. But if we simply apply this method, then computationally it will be very expensive. And the reason is very simple, because if we want to apply this LETKF, we need to run our entire system forward for multiple times in order to get all those ensembles. But each time when we run this DEM, run this QG model, it itself will be very expensive, because for QG, for example, it is 128 times 128. We need to run this entire model for many times. So computationally, it will cost a lot of time, and it will be very expensive. So the new idea here is we try to develop some simple forecast models, but these simple forecast models will have similar forecast and data assimilation skill as the original model. This figure illustrates or summarizes the main idea of this new method. So we start from the model in the physical domain. you can just think this is a discretization of the QG model. I use minus pi to pi here. This is just for some illustration purpose. And you can think each dot is a grid point in ocean, right? So this is basically the model simulation from the QG model. So the first step here we want to do is we want to apply a Fourier transform. So we no longer need to deal with the physical domain solution, while instead we will focus on the Fourier domain. So again, here minus 16 to 16 just for illustration. So in your model, it should be minus 64 to 63, something like that, right? So from physical domain to Fourier domain, what we need to do is we just apply the FFT or any Fourier transform at each time instant. Then we try to look at the energy spectrum. We know for those modes that is very far from the center, they will have very tiny noise. So actually for forecast, we do not need to take into account those modes. So we draw a circle here and we include all those energetic modes. Then we apply a reduced order system, which only includes those Fourier modes that have certain energies. So basically, we ignore all those things which contain tiny energy. And this is second step, but only with this, that's not enough. So what we do next is, now instead of considering this totally coupled system, what we do is we try to model the time series of each Fourier mode in an independent way. So you will ask me here, how can we do this, right? Because in principle, all the variables in different grid points, they will couple each other. So all the Fourier modes, they will also couple with each other. So the key trick here we use is the forecast uncertainty due to the nonlinearity between different Fourier modes will be replaced by the stochastic noise. Basically, we start with a complicated nonlinear model. Then we drop this nonlinearity, but we put additional stochasticity to compensate its effect. And remember, when we do data simulation, in the forecast stage, we only need to run our forecast model for a short time interval, right? So that's why this stochastic trick can be applied to compensate basically all the nonlinear effect to describe the uncertainty for this one-step time evolution. And this will be a very important trick because now we can completely ignore the coupling between different Fourier modes, and the stochasticity will describe the correct time evolution of the uncertainty. And as a result, all these Fourier modes, they will become independent with each other at each forecast stage. And the reduction of this nonlinearity will be very important because it facilitates the Lagrange data assimilation. And then the next question is how to model each of these Fourier coefficients. So here we first just need to judge if the statistics of this Fourier coefficient is Gaussian or it's non-Gaussian. So if the statistics is Gaussian or if it's nearly Gaussian, then we simply use a linear process with constant noise coefficient, which we call that additive noise, to describe the time series of this Fourier mode. And this is also called Ornstein-Uhlenbeck or OU process. It's a linear Gaussian process. While on the other hand, we know ocean and atmosphere, they are both turbulent. So there will be certain modes that are highly nonlinear or non-Gaussian here. Like for this one, we have these extreme events. So the statistics are not Gaussian. Then using a linear Gaussian process will not be a suitable choice. So here, what we do is we still use a linear process, but we use a multiplicative noise here, which means the noise coefficient will depend on the state variable. So with this non-constant noise coefficient, then we are able to capture the non-Gaussian statistics. So although this may look a bit complicated, actually all the parameters in both equations can be determined systematically using closed analytical formula. And we call this data-driven method because we first look at the time series of each Fourier mode, then we use this time series to determine the coefficients here. So everything here can be determined using closed analytical formula, including this multiplicative noise coefficient. And therefore, we can have no bias in determining the parameters. So there will be no ad hoc tuning, no empirical choice. Everything will be systematic and analytic. So running this kind of forecast model will be very cheap, very efficiently. Another advantage of such method is when we consider a Fourier domain data assimilation, then the coordinate transform will not be a problem. Because when we transfer from the Eulerian coordinate to Lagrange coordinate, we can make use of the Fourier basis. So there's no need to do any empirical interpolation method. So everything will be rigorous and analytic here. So before we show all these results, I just want to do a quick comparison of the computational cost. So if we want to run the original QG model, the ocean model, then as I said, we use 128 times 128 resolution in order to guarantee we have sufficient enough resolution for the small scale eddies. But by doing so, we need like 16,000 modes in total for each run. We cannot just truncate them in a forward model because although those small scale has very little energy, it will contribute to the dynamics. If we do a Bayer truncation, then the system will blow up or will give us completely wrong solution. But when we do the reduced linear stochastic models in the Fourier space, then we can keep all those energetic modes because those nonlinearity has already been replaced by stochasticity. So we don't worry about the feedback from the small scale to the large scale because they have been replaced by the stochastic effect. Then we can do a truncation. If we say we truncate up to k is less than 16, which actually covers more than 99% of the energy, then the resulting reduced order model only contains like 200 modes. And also, all these linear models, they can be run independently, and they can be run in a parallel way. So in that sense, this 200 compared with this 16,000, it's only like 2%. And also, we can run everything independently. So computationally, it's much cheaper by using these linear stochastic models with either additive or multiplicative noise. Also, we can compare the accuracy of this strategy with the original system. So here we show two curves. Both left and right side columns are the scale scores. This is RMS error. This is pattern correlation. So this blue curve is a case where we have this QG model as a truth, while we use a linear model with additive or multiplicative noise as a forecast model for data assimilation. So the x-axis is the number of the flows. While this purple curve, it is like a twin experiment. So we use a linear stochastic model as a truth, and we use themselves as a forecast model. So of course, a better illustration will be we use the QG as a truth and also with the QG as a forecast model, but that's too expensive. It's impossible to do this experiment, and that's why we use this alternative twin experiment. But these two curves, they are pretty close to each other. And actually, the twin experiment even gave us a slightly worse result because stochasticity, we use that as a perfect model, may have a slightly shorter memory or a bit more turbulent behavior. So the error here is slightly bigger, but overall they have similar behavior. So this means if we use this simple strategy to replace the original complicated model, then we can save a lot of computational cost while we can retain almost the same accuracy as the original system. Okay, so now I want to describe the data assimilation results. So for the setups here, we consider only the non-interacting flows. So we don't need to worry about the complicated contact force in the modeling side. These flows are randomly drawn from a library that are based on the observed flows in the marginal ice zoom. You may get more information from Monica or Georg's talk. about this part. And for the observations, we observe the linear displacement or the location xy. Also, we observe the angular displacement, basically the angle at 2 time instant. So this omega here. And this is very different from the traditional Lagrangian data assimilation, where only xy can be observed. And in our standard test, we have 30 flows, but later we will change this number to see what will happen. And in total, we assimilate 50 days, which mimics the Fourier summer. And all the statistics are computed based on result from day 10 to day 50, because the first few days can be some relaxation time. And since we just arbitrarily assign some initial condition. And in the standard test, we assume the observations are obtained once every day or every 24 hours. So for results, first, I want to show that it's necessary to include this multiplicative noise in our forecast model. So in this figure, you can, especially the first panel, you can see this is a time series for the atmosphere wind of the mode 0, 1 in the horizontal direction. So just by eye, you can see a lot of these intermittency or extreme events. And if we look at the probability density function, then this black curve, which is almost overlapped with the red curve, has these very fatted tails. The blue one is a Gaussian fit. So you can see the two PDFs are very different, which tells us the PDF of this one is highly non-Gaussian. Then we use our linear model with multiplicative noise to model this part or to approximate this kind of signal. And this is just a free run from the model. So you don't expect point-to-point match. But what we expect is the PDF from this time series match the PDF of the truth very well. They overlap with each other. And also here, we show the multiplicative noise coefficient. And you can see that this sigma u here is not a constant. Actually, it changes a lot as the value of this u hat here. So this means it's necessary here not to use a constant. And if we use a constant, then this will be the result. So this is the result from using a linear model with a constant noise. And by doing so, we basically kill all the extreme events. So this is definitely very different from the truth. And for another atmosphere mode, similarly, but this mode, it does not have fat tails, but it looks like a sub-Gaussian. So the tails is much narrower than Gaussian. We have a similar result. But both cases tells us it's necessary to use a linear model with multiplicative noise in order to deal with all these non-Gaussian features. Okay, so next we try to look at the truth, compare the truth with a filtered result for the flow velocities. And here we just randomly pick up 3 flows. The blue curve is truth. The red one is the filtered mean of the flow velocity. And actually the filtered flow velocity is quite accurate, right? So you can see the error is very small. The pattern correlation can be maybe 0.9 or even more. And this is also easy to understand because we can observe the locations of the flows. So the velocity basically is a finite difference or the derivative of these locations. So that's why the flow velocities are usually very easy to recover here. But on the other hand, for recovering the ocean atmosphere, that will be more complicated. So here I show first the recovery of a few Fourier modes. The left 4 panels here shows the recovery of the 4 most energetic modes of the ocean. And these are the recovery of the 2 atmosphere modes. So these 2 modes, they are varying in a very slow path. So overall, our filter results are quite good. And these 2 are slightly faster. Filtering is not too bad, but of course, comparing with the flow velocity, it is slightly worse. Then for the zeroth atmosphere mode, this is basically the background mode. So it is quite accurate, but for the next atmosphere mode, it's much faster. So we can see some errors here. And by the way, these values are non-dimensional values. So you will see some crazy values. Also, this may seem to be much smaller than the ocean, but we use different non-dimensionalization. So still, this mode will contribute a lot to the total dynamics. Then we can look at the physical domain recovery. So we show the ocean field of the truth at day 20 here, and this is the truth of the ocean at day 30. You can see some larger scale features and some small scale eddies for the ocean velocity here. And these two are the filtered mean at day 20, day 30. It's not perfect, but we can capture some larger scale features, especially those big eddies here, and also some small eddies with pretty decent recovery scale. And this one shows the recovered uncertainty. And all these dots are the sea ice flows at that time instant. So these are sea ice locations at day 20. I only show the central mass. Otherwise, it's hard to see the ocean field. So the uncertainty here is not too big, because if we take the square root of this 5, it's basically 2 point something, while the actual ocean field is like 10 or 12 kilometer per day. And also, we see that when we have these observations, sometimes we have pretty big uncertainty, sometimes we have small uncertainty. So maybe you will think if we have observations, then the uncertainty will be smaller. But remember that we use a Fourier domain method, so the uncertainty is in a global sense. So even without observations, at some places we have small uncertainty, but some places we have big uncertainty. Okay. Then the scale scores. So we show the root mean square error and the pattern correlation. And in the first column here, x-axis is the number of the flows we can observe. And there are 3 curves here. The blue one is the one we can observe both x, y, and the angular displacement. And for this green one, that's the case, we can only observe x and y. Now you can see actually they have a difference here. This means observing this angular displacement is very important, because it will provide us additional observational information. And in fact, if we have 30 observations for x and y, this part, it is essentially the same as we have 20 observations for x, y, and omega here. So this means basically the role of this omega is similar as x, y in providing us the information. And there's another curve, which is the sine curve. That is the one without the atmosphere wind. So basically we want to test if atmosphere wind will give us some positive or negative effect. But this one, it's almost overlap with the blue curve. So here, because atmosphere wind happens in the very large scale, while ocean is in the meso scale and sometimes a small scale. So this atmosphere wind, it will not break or will give benefit too much for data assimilation. So with atmosphere wind or without atmosphere wind, the recovery scale of the ocean is basically the same. And this one is just to check the data assimilation scale with ensemble size. So of course, with a very small number of ensembles, we will not get good result, but then this curve become flat after a certain threshold. And actually for all the tests we do here, we use 200 ensemble members together with the localization. So 200 gives us a pretty decent result here. Okay. Then for this one, we want to look at the scale of our data assimilation in recurring different spatial scales in the ocean. So x-axis here means we do a reconstruction of the ocean field up to this k absolute value. So for example, here we take all the modes k that is less or equal to 4 for the reconstruction. And this basically gives us a reconstruction of the larger scale or the larger scale plus mesoscale, where up to here, we do the reconstruction for almost all the modes. And this column shows the reconstruction of the velocity field of the ocean. This one, the right column, shows the recovery scale of the vorticity of the ocean. So for the velocity, actually, the first few modes, they have very low energy. So the resulting filtering result is not as skillful as those large to medium scale, because the signal to noise ratio is pretty small here. So the best thing is we can recover the scale up to maybe k equals 4 to 6 for the velocity. But for the vorticity, you can see the scale decreases almost monotonically as we include more and more modes. So this means for the vorticity, we can do the larger scale the best, then the meso scale, then the small scale. And again, this red and green curve shows we use the observations, including the angular displacement and excluding the angular displacement. So using angular displacement will give us some additional beneficial effect here. Another thing we can check is usually in the Arctic region, sometimes there will be a large piece of a cloud which will cover a pretty large area. So when there's a cloud there, it's impossible to observe the sea ice floes because the satellite cannot see something under the cloud. So here in the top figures, we show that if we have 30 observations at the beginning up to time day 16, then afterwards, we have clouds that covers half of the region for 3 days, for 5 days, for 7 days, for 10 days. Then how the data assimilation scale will be. So of course, if the cloud only lasts for a small number of days, then the result will eventually go back pretty quickly. But definitely when it go back, it will take more than 3 days for the adjustment. And if we have cloud for 10 days, then basically here it will take almost 20 days to fully adjust back to the normal status. And here we show a comparison of day 20, which is here. In the top panels, it is same as the previous figure. So we show the truth, the filtered mean, the uncertainty with all the 30 flows. But in the bottom panel, we show the truth, the filter, and the uncertainty with only 15 flows. So the other 15 flows, which are in blue dots, they are covered by the cloud. Then we can see the overall scale is slightly worse. Also, you can see from this RMS pattern correlation. But for the uncertainty, you can see now, even if we have no observations in this entire domain, the recovered uncertainty here is comparable as uncertainty with observations. So again, this helps us to understand that this method is a global method. It is based on the Fourier basis and the Fourier data assimilation. So even if we have a certain area that has no observations, we can still get decent recovery at this area. So like here, the scale is basically similar to here with observations. So the last result I want to show here is the importance of this multiplicative noise. So although previously we showed that multiplicative noise is important in capturing the non-Gaussian feature, here I want to show that multiplicative noise is indeed important in data assimilation. So here the truth is the blue, which is the same. The left panel here, we have multiplicative noise as in our linear model. And in the right panel, we have only additive noise. And what's significant here is with multiplicative noise, it is more skillful in recovering the extreme events. But additive noise, it will very likely miss or underestimate a lot for the extreme events. And the reason is also simple because multiplicative system, it has this fat tail. So when you do the forecast, it's much easier to forecast, or it has a high probability to forecast the extreme events. So since a multiplicative noise process and additive noise process, we can both determine the parameters using an analytical formula. So it's better to include this multiplicative noise here. Okay, to summarize, so in this talk, we develop a new efficient and statistically accurate data-driven Fourier domain Lagrange data assimilation strategy. And we show that its multiplicative noise is essential to capture the non-Gaussian features of nature. And we also show that 30 flows gives us a pretty decent data assimilation scale for a domain with 200 times 200 kilometers. We also show that different from the traditional Lagrange data assimilation, we have this angular displacement, and it is indeed helpful to improve the data assimilation skill. And we also tested the uncertainty. So the areas without the observed flows may not necessarily have higher uncertainty because we use this global Fourier basis. And data assimilation scale of the velocity is the best at the spatial scale of k equals 4 or 5, while the scale of recurring the vorticity is best at the largest spatial scale. After that, it decreases monotonically. And so basically, that's all what I want to present for this Lagrange data assimilation of the DEM models. And thank you very much. So feel free to let me know if you have any questions or comments. So thank you.